let's focus again. Have you heard some interesting statements about what was surprising to you? Everything quite common? Something surprising?
Verify your assumptions on your blog posts. I mostly do stuff with the hope of that it happens like I would want it to happen, and if it doesn't, I'm kind of, why doesn't it work? So I don't really have verification mostly before I start.
Yeah, it's verify assumptions is usually we have a lot of assumptions. Without assumptions, I think we talked about it at the very beginning of the course. Without assumptions, learning is impossible. But often it's important to verify your assumptions. I don't say that this is easy. It may take quite a lot of time to verify your assumptions. But often, if your thing doesn't work as predicted by yourself, the problem is that one of your assumptions doesn't hold. So it's one of the things how you can debug something. Actually, when I asked what was something did something surprise you, somebody shook violently his head. This is actually what should happen if you already gained some experience in machine learning. I gave, I think the one from Carpati I gave to my PhD students, the more advanced ones, and asked them to please read it. And they told me, yes, we read it, and was it interesting? Yeah, it was interesting to see basically the same things we also discovered. They said 80% of the stuff they basically also found out, but it took them some sleepless nights and some pain over the last 2 years. So this stuff really is a stuff that makes you succeed in practice. May I ask who read the article by Carpati, the one on deep learning? Which one of you had a look into this one?
Which one is it? The first, second?
The first one here, yes.
First.
Okay, who looked into the one on reinforcement learning? This is this one. Okay, so lots of more people reading that. Anyway, side note, I just realized that yesterday while putting it on the slide, this guy is studying to pursue a master's degree somewhere else in Zurich. So this is actually the level you're compared with on the job market, just as a side note. What do I want to say with that? I don't want to scare you. I just want to tell you it doesn't matter if you have a PhD, if you're a professor somewhere, if you're a senior, whatever. You can produce very, very interesting results and stuff that is very readable and helpful for others, regardless of the level of your latest degree. This is what I wanted to say. Okay, and who read my post? You took the shortest one, but the one with the least details. So if you're doing some thesis on deep learning or reinforcement learning, look into the others as well. Okay, any other thing you wanted to say about these things? Yes?
They all discover quite the same thing, I think, but I never read in this article or even in discussion here. If you start with something, I think you have to start with discovering, even in the internet or something else, if someone was already, or if someone has a similar problem to you, so you find probably already some start off you don't have to make the same mistakes again.
Yes, you should always start with the literature research or a code research, and you should start with a reasonable baseline. I think one of the reasons this is not mentioned, at least by Carpati, the first one is that he is talking about doing original research, which by definition means you're working on a problem nobody has worked before. But yeah, normally that's a very good thing. Look what others have done and build on top. And still keep in mind, don't start with a very fancy thing. Start with something even rudimentary, something very basic. That's quite important, and then go step by step and verify each step. Okay. I promised you that we talk today about system development, the whole pipeline, not just a single algorithm. Now we talked a lot still about how to prioritize algorithmic work. We will now focus more on the larger picture, as I promised. But I didn't want to spare you these practice tips because I think you have to get in touch with these if you haven't before. Good. So, as we move towards a whole system, we also change our example. Now we're done with text analysis, we go to a different example, and the example comes from computer vision. Document analysis, it's about reading checks. And the example comes from the 1990s. I'm not sure if people in the US still pay with handwritten checks, they do. So it's still, okay, the example at least still valid. It's about finding the amount and reading it automatically. And the problem with checks is they all look different. They all have different layouts. People have horrible handwriting. Still, people succeeded in the mid-90s to build a check reading system that finds the right amount, reads the digits, and does it fully automatically for at least 50% of the checks in the US banking system. Mid-90s. What we will do now, we learn something about system design by looking at this example. First, I want to make you aware of a technique that helps you to prioritize where you focus on when you have a huge pipeline. What do I mean with pipeline? In the example we have here, we have an image. On the image, we need to do text detection. Text here also means digit detection. We need to detect where is handwritten text. Then we have to segment the different characters. And then we can recognize different characters. I'm aware you could cut these different steps differently, but this is one way you could do it. And usually you have such a pipeline in machine learning systems. And the question is, and usually you have some post-processing, like when you recognize the characters, you do some sanity checks, if that is really an amount, and so on. But usually you have such a pipeline. The question is, which step of the pipeline we should focus on, given that we have limited resources and we want to improve as much as possible? What could we do? And the technique is, again, very a standard thing. It's not fancy at all. You just have to keep it in mind when you're working on something. The thing is called ceiling analysis. And you look at where in my pipeline do the most errors appear. How do you do that? So you have your pipeline. Remember, you build the whole pipeline, the complete thing, during the initial 24 hours, plus minus, of your project, right? This is why you hack it together in the beginning, that you already have the full pipeline. Doesn't matter how well each step works. Important thing is you have the whole thing. So you have the whole pipeline, and now you measure the cross-validation performance of it. Let's say you do 72% correct, the whole thing, your system. Maybe not after 24 hours, but after a couple of weeks. Good. Now you want to know, should I put my resources to text detection, character recognition, segmentation, whatever. What you do is, you replace, starting from the beginning of the pipeline, moving towards the end, you replace one after the other box by a perfect system. Perfect system? Yes, you cheat. You just take the ground truth and plug it in. You build a dummy software component that takes a ground truth and gives it as a result to the next. It's some software engineering work, but you need to engineer that, but arithmetically it's super simple, right? So you take perfect result for here, and then proceed with what you currently have. Let's assume when you replace text detection by a perfect result, you move from 32 to 89% accuracy, which is pretty nice. And let's continue. Let's also replace character segmentation, so text detection and segmentation by ground truth, and just do character recognition by your current component. Let's assume you get 90%. And let's do everything with ground truth. Of course, then you should be with 100%. So, what does it tell you? The interesting thing is to look at the deltas. The improvement of improving text detection is 17 percentage points. Then the improvement, if you are better at character segmentation, is just 1 percentage point. And again, if you do better with character recognition, you improve by 10%. I would wish that I would have looked for such things as a PhD student, because I've spent years in improving a thing like character segmentation, which is nice. You can write like it wasn't character segmentation, but something with the same value. you can write papers on it, you can do a lot of interesting intellectual stuff, but in the end it doesn't matter. If I do perfect or if I suck on this task, contributes 1% to my total success. So if you have a little bit more pressure in the system and you're forced to focus on results and don't have time forever, you would rather improve text detection because it yields the most improvement. After that, probably character recognition. If you still have time, you can do something for segmentation. This is called ceiling analysis. It's just applying the rational mind. I think this should be common sense. But anyway, this is how you think about the pipeline of your system. Analyze each thing, see what does it contribute to your final success, focus on the parts where you can improve most. Of course, there are other things that flow into it. Do I have a good idea to improve it? Is it reasonable to improve it? Do I have the data? Is there some leverage to really do something there? All this also needs to go into it. But first thing is to see where does it actually matter to your effort. Is that okay for the moment? What I'd like to do now is to take you on a tour through the check recognition system. I tell that up front. The details of the check recognition system are not to be memorized or something like that. I will not ask you in the exam like how does this algorithm work. So we want to look into a larger system to see what did they do in order to engineer the whole system to make it better. Right? So try to follow me on these big lines. If there are some details you currently don't understand, of course you can ask, but it's not that I will ask you details about that. That's not the plan. Good. So, learning to read checks. It's actually a great paper. It's this one. Gradient-based learning applied to document recognition. This is the paper by which I understood convolutional neural networks. Probably nowadays there are more and better and more geared towards beginners resources. But when I started learning about deep learning, I took several approaches to try to understand what does a CNN do, what is it. And it was actually this paper that put it into a context and explained it in a way where I put the intuition and the math and the code and everything together. Oh yeah, cool, that's it. It's from 1998. It's a huge journal paper. It appeared in the Proceedings of the IEEE, so the journal of the IEEE. It's almost 50 pages long, talking about a landmark article. Like this is when a great team of a big research project reports about their great and final findings after a couple of years. So there have been a couple of previous publications talking about the same kind of stuff in shorter versions. This is the big overall version. What does it talk about? It talks about gradient-based machine learning. We did that, I think, in lecture 2. We talked about gradient descent, not for neural networks, but for some other algorithms. But we basically know what gradient-based learning means. We optimize by taking steps into the direction of the gradient. Then it talks about convolutional neural networks. It's basically the article that introduces a convolutional neural network that shows good performance on endless. It introduces the famous LeNet 5 model, and the Le comes from the name of the first author, Yann LeCun, who's currently the director of AI at Facebook. Joshua Bengio is also one of the authors. Those two are among the 3 most famous deep learning researchers worldwide. Good, then there's another chapter. This is the outline of the paper. Comparison with other methods. Okay, you need to have it in the paper, it's not so interesting here. What we will talk about is these 2 middle stages, because I assume you know something about convolutional neural nets or you can treat it as a black box. We will talk about these 2 chapters that basically talk about how to extend a CNN that takes in an image and says what it sees in the image and build a whole system that can read checks. So imagine you have a classifier takes in an image with a single number digit on it, can tell you which digit to a high degree of accuracy. Taking this, scaling it up to a whole system pipeline. This is what we were talking about. Checkmate system. Disclaimer. These so-called graph transformer networks that they present here, they haven't been adopted widely. I was actually looking a lot into that, and there were only 2 or 3 publications that used the term afterwards. And 2 of them were by the same authors. So it's not that this is a famous thing, the graph transformer networks, that we need to know, but they discovered a principle that is basically the underpinning of all end-to-end deep learning we have to do. Today it's done in a more simple way than they described it here, but it is of some value to see what is behind. But it's an historical example. It's not an algorithm for your toolbox. Right? So, why do we need to talk about that? Because we have, when we want to detect a number, so a sequence of digits, we have a sequential machine learning problem. But what we usually look at, and what we looked into in this course so far, is standard supervised learning. You know the setup. This is an image of the table of entries in the famous, what's it called, the IRIS dataset. The IRIS dataset is one of those famous datasets for data mining. It's like ImageNet 20 years ago, not with images. It's every row here is a record, and it's about some measurements on plants, and you can basically classify it into 3 different forms of the plants. This is what we have in supervised learning. We have a table, every row is a record, we have a label here, and we treat them independently and identically distributed. That's an important point. Independent, that means the order of the rows plays absolutely no role. We have that in support vector machines and decision trees and random forests and all the methods we looked into so far. We treat the data IID. And that is a problem as soon as the data is not IID. Consider speech. We can convert the speech waveform to a spectrogram where each column here is a feature vector, but the columns are not independent of each other. When I shuffle their order, they have the same statistical properties, but you cannot recognize anything by your ears. So obviously the order plays an important role. So if you have sequential data, you probably have to do something about it. Otherwise you will miss vital information that is in the sequence of the data. So what can we do about it? There are several approaches how you can handle sequential classification problems. Let's talk about the smallest, let's say the bird in the hand approach. In German that would be die Taube in der Hand, der Spatz in der Hand. The bird in the hand approach, the simple one. That is, train a standard classifier, standard meaning it treats the data as IID samples, and then use a sliding window or some post-processing to basically superimpose some order constraints. For example, you could do that on speech. You move a sliding window over it and you say, I classify what is under the sliding window and ignore the rest. You can always do that. You can take a standard machine learning approach, treat what is under the sliding window as not sequential, but just one feature vector, ignore the rest, and you will do work. You could do a more, let's say, physically or reality motivated approach. For example, you could train a generative, statistical model of the sequence, like a hidden Markov model. Who knows hidden Markov models? Who has heard about Gaussian mixture models? Think about a Gaussian mixture model and a model on top that says in the first state we have this Gaussian mixture model describing the state, and then there's a transition probability to a later state where we have a different Gaussian mixture model that describes the state then, and then we have transition probabilities into two different states where we have other Gaussian mixture models. So it's a sequence of GMFs. One way to describe a Markov model. That would be modeling what is really physically happening in a statistically very sound way. that has its pros. It's a very sound way of doing it. It has its cons. It's quite complicated to learn. Like, not for you to learn, but it's complicated for the machine to learn the parameters. It's a complex process. And then there's, of course, the second part of the same, the Taube auf dem Dach approach, the two-in-the-bush approach, which means we could build a pattern recognition system that is designed of specific steps. It's a pipeline, but we could train it end-to-end. And we could have a global constraint that looks for the final result independent of what is actually happening in the different stages. There are a couple of reviews if you want to go further into sequential data processing. Up to 3 years ago, I found this one from Thomas Dieterich from 2002, a quick review what is around in sequential modeling. I had another look yesterday, and of course there's something specifically for deep learning, for sequences. If you have not taken the module, there's a specific module in the MSE on time series analysis, also with deep learning. Have a look here. Okay, that's the underpinning of the problem. We will have a sequence of digits on those checks, and we are not already okay when we recognize each single digit. We want to recognize the amount, and that means we have to recognize the digits in the right order. So we have a sequential decision problem. How can we do that? We will take this string with a 342 as a running example for the next couple of slides. What do we want to do? We have a pipeline of a couple of steps. First, let's assume we have detected this part of the image where we assume the numbers are. Then we need to do the following. And still assuming we have a CNN that can recognize single digits. We have to segment that into candidate digit images, and we have to recognize what is on each single snippet. And then we have to assemble the recognized digits to the final amount. 3 steps. Segmentation, recognition of single digits, assembling it together. And what we want to do is, we want to build an end-to-end system that is not optimizing on its own segmentation, and then the digit recognizer, and then the assembly, but that is just looking for the final result, and everything else is adapting to each other. This is, to take the conclusion already now, this is the benefit of doing things end to end. You don't have to have intermediate results where you fix the API, so to say, between the pipeline parts. You don't have lots of intermediate goals where you need ground truth for and that you need to define. Just define the end goal, and you let all the other stages in your system, even if you pre-model it as stages, you let them adapt to each other and also communicate with each other where they want to make the handshake. If the segmentation module is not splitting it like this, but rather like this, but the recognition module then can assemble it together anyway, you're fine with it. You don't want a perfect character recognizer here. You want a perfect check amount reader. So you're solving actually a simpler task if you let these stages adapt to each other. Okay? What's that? You know what I mean? Not saying no means yes? Okay. Let's quickly go through it. A traditional way of doing it, and that definitely holds in the non-deep learning area. I think it still holds when we're talking about also doing deep learning stuff. A traditional approach would be to build different systems for the steps in the pipeline and optimize them separately. Maybe even let different teams work on those. You have a team working on the field locator, like where is the amount? It's here. A different team on the segmentation, like what are the different characters. A different team for recognizing what is a character then. A different team for assembling everything together. This is what here is called the Linguistic Contextual Post-Processor. It has a grammar in it. It knows For an amount, we don't start with a 0 and stuff like that, and then we're fine. With all the problems that I just described. The field locator has to be perfect. The segmenter has to do exactly what we think a segmentation needs. Originally, we only want a good position. So, what Lecan and his colleagues proposed is, yeah, we might have still the same steps in the pipeline, but let's put that all in a way that it has one set of tunable parameters that could be tuned by gradient descent. We don't assume anything else. We don't assume these are neural networks. We don't assume anything, but they are parameters, and we can take gradients with respect to these parameters. And then we get an output out of this whole pipeline. We don't care about the output here, the intermediate results. Let's ignore it. We look at the final output. We compare with the final ground truth. We have a cost function or a loss function. We take derivatives with respect to these parameters. We do gradient-based updates to all these parameters, and we should be fine. And specifically, we don't need ground truth for these steps. And specifically, we don't need to very precisely define what exactly the segmenter is supposed to do in order for the recognizer to work. It will adapt to each other. We don't have intermediate losses here. So this is what I mean with end-to-end learning. Let's look a little bit into this, just to get an idea of what's happening. Foundation is gradient-based learning. You already know this. You have heard about gradient descent if you heard about deep learning. You definitely heard about it at the beginning of this course, where we talked about the linear, what's the word? Regression. Linear regression, thank you very much. We trained that by gradient descent. So, assume the following. You have some input, in that case Z. You want to have some result, B, Ergebnis, I don't know. We could have a lot of different blocks that do something to this data, that transform the data in some way in order to come to the final result. The only thing we need to assume in order to do gradient-based training is that each of these blocks can do a forward pass and a backward pass, can actually pass data through it, and can calculate a derivative with respect to its parameters, W. If that is the case, if we can guarantee this, we do not need to know anything else about the architecture of these blocks. We can just put them together. This is a very fancy thing from the perspective of the mid-90s. This is exactly what you do today if you're doing a little bit in deep learning. And you know, I could have this convolutional model here, and I put a classification layer on top, and then I put a GAN loss to it to regularize it, and make it fully convolutional to put out an image in the end. You're stacking components that are trainable by the same algorithm, by gradient-based learning. This is how they proposed it. And here it still looks a little bit more general. It's not focused on neural nets, not at all, even if they use neural nets. Interesting observation they make in the paper. It very much suits an object-oriented approach to machine learning development, because each of these things could be a class with two functions, a forward propagation and a backward propagation functions. When those functions know what to do, the rest for you as a developer can be a black box. Okay, so we have components and we know they can do backward. That's it. What we call these thing, such a thing, is a graph transformer. Something goes in, it is transformed to a final result. Why? So this is why it's a transformer network. It's a network of things, it transforms something. What does it transform? It transforms a graph. What does it mean? Usually, this is what we see here. Usually, we don't have graphs as input to a machine learning system, right? Usually we have vectors as input. A vector has a fixed size. It's basically an array. And you put it through, and always the input and the output are vectors. It can degenerate to a scalar in the very end, but in the end, in machine learning, usually we deal with vectors. What the authors here proposed is to have a different data structure, namely a graph. Why? It's a little bit more flexible. For example, it allows different sizes. It does not have a fixed size. What is a graph? In this case, a directed graph without cycles. It has a beginning, it has an end, it has arcs between the nodes, and there can be metadata attached to the arcs. They defined their overall system structure in a way that the different components, the steps in the pipeline, were differentiable blocks that took in a graph data structure and put out a graph data structure. What could the data structure contain? Let's imagine the following. We have a graph structure here, you see it. The nodes are different segmentations of the image. This is the original image. So every node is a specific, partially overlapping segmentation of the image. Every single path through the graph reassembles the original image without any overlap. So the different paths through the graph are the different ways how to segment the image. And the metadata attached to the arcs is actually a penalty. So the inverse of a confidence, how sure you are of that specific segmentation. You can see here, this is the correct number 4, the digit 4. And the penalty is very low, meaning that the system somehow is very confident that this is a correct segmentation. This is a part of the 4. This is obviously wrong for us. And likely, this image belongs to this node, the arc also has a very high penalty, so the network is not very sure that this is a good segmentation. So here you can see at this example why they use graphs as input structures. It's quite flexible. You can put in something like a complete set of segmentations in one single data structure without fixing dimensions. So far, so good? Remember, we are not talking about not proposing that you should use that in your method. It's just we want to see how a good example of an end-to-end design system. So here, they use these graphs as inputs. Now, let's imagine one way of how this could be built. The G things here are graphs, like inputs and outputs of the system. The T's are transformer blocks, like parts of the pipeline. Input to the whole thing could be an over-segmentation of the image. A segmentation in all possible ways. How can you achieve that? You could do it with a sophisticated algorithm. What they do is they over-segment heuristically. They have some simple rules like if two lines are not connected, just segment it there. And put all possible segmentations in the graph. This can be done by a quick and dirty hacked algorithm, quite simple. The only assumption is that the real segmentation will be among all the segmentations that occur. Now this is input to what we would today just call a computer vision CNN. It takes a single image patch and tries to recognize what number is on it. So basically a deep neural network trained on MNIST. This is actually what they did. They collected MNIST for the sake of this project. So every image from the graph is given to an instance of the CNN, and it transforms the graph. We still have all the different segmentations, but for every arc, meaning for every possible image patch, we get penalties for all possible interpretations of that image. So this is obviously a 3, right? So it would say give probably a low penalty for the real 3, but it will also give penalties for all other possibilities, like for a 1, a higher penalty, for a 2, a higher penalty, and so on. I mean, there are only 9 possibilities because we have 9 digits. Oh, sorry, 10 zeros. So we transform the graph with the images, another graph with probabilities for every possible recognized digit. And now we put it into a transformer that is actually not a neural network. The only thing is we need to take derivatives of it. They call it a Viterbi transformer. Who has heard of the Viterbi algorithm? Just heard the name. Anybody wants to explain it in 2 sentences? Okay, I tried, you can correct me. I'm not an expert on that. But I read some things about speech recognition, and it's an algorithm you, for example, need when you do hidden Markov model-based speech recognition. The Viterbi algorithm basically takes as input a graph, and has annotations as probabilities or penalties, whatever. And the Viterbi algorithm is a very quick and efficient algorithm to give you the shortest path through a graph. And short here means the one with the lowest penalty. So you need that in speech processing, and you have different interpretations of the sequence of sounds you receive, and you want to know which sequence of sounds which interpretation of the sequence of sounds has the highest probability, given a language model and the acoustic probabilities and so on. So they have a transformer built on the Viterbi algorithm that takes in this big graph with all the possible paths, with all the possible interpretations of every segmented image, and this one just gives out the one with the highest probability. You could do it very, very simply by just counting. The Viterbi algorithm is just doing it in the most efficient way. So it's nothing fancy. Out comes a single graph, a single path through the segmentation with interpretations on it. We can sum up all the penalties, and this is the final confidence in, or anti-confidence in the result. This would be one way to implement it. And actually, how this works in detail can be seen on that image, but I think we don't need to go much more into detail here. A last thing I want to show you based on this example. And this is how the authors of the paper took a very crucial choice, and this is the choice how to train such a system. I mean, if you have different components of a pipeline, segmentation, recognition of characters, assembling the characters together to a whole number, every task itself is quite complex. You want to train it end to end. There are a lot of ways how machine learning could fail here. You probably gained enough experience by now to see that this is a complex system. And there are different ways how you can use the available information as a learning system, as a learning signal, as a signal to inform the learning of the system. What do I mean with learning signal? Basically, what do you provide as a loss function? How do you count the errors? What information do you put in to actually base the gradients on? Because this is the only thing the algorithm sees to adapt the system, right? And there are several ways to do it. And the authors had 2 ideas how to do it. And what did they do? An ablation study. They implemented both, they tried both, and they tried to find out which one works better. Let's first have a look on the half detail level. What would be the simple version? The simple version would be, we have all the stuff we saw on the previous slide. So we have the heuristic segmentation, we have the different CNNs that recognize what is on each image, and out comes the graph with all possible segmentations, and we have segmentation penalties as meta information of the arcs, plus the penalties for all the different interpretations on each arc. So we basically have all our results in that graph data structure. What do we do now? And they said, the simplest way to do it would be to look into the ground truth to see which one of the path is actually the correct one. And we could use this ground truth to constrain the interpretation graph, this one, to only those graphs that contain the correct sequence. What do I mean by that? Some of these paths still lead to the correct sequence 342 of the digits, even if they don't have the correct intermediate segmentation. So these paths they would keep here. But there are other paths that lead to a wrong result, not to the result 342. They would kick them out. So they said, we use the ground truth that we have to kick out all the paths that are not correct, constrain the interpretation graph to only contain those graphs that are correct up to this point. Then we use this Viterbi transformer we talked about on the last slide, the one that just calculates which one has the lowest penalty. We take this one, and the final penalty, like the inverse confidence, is the score, the sum of the penalty of this selected path. And then we can use this to calculate as a loss function value, can calculate gradients with respect to all the parameters of all the algorithms. We can adapt these parameters. They tried this out, and you can read more about it in the paper. It worked, but it didn't work too nicely. But I mean, it looks very much straightforward, and you use the information you have, you use a ground truth. Why didn't that work? Well, what they said is, I've put here just for if somebody's interested how to take gradients, but we will not go into that level of detail here. The problem is this solution can come up with trivial, like the machine learning algorithm that uses this way of training, can come up with trivial solutions. It can completely ignore all the data you put in and just produce a result here that always puts out something with zero value. This will reduce the loss to zero. So the optimization will succeed, but what you actually want to recognize what was put into it will not succeed. So the criterion is set in a way that the algorithm can learn to cheat. That's not what you want. You don't want your algorithm to cheat. And the other problem is that if you have different solutions that would have been correct, only a single one is scored in the end. So all the competing answers are not taken into account. The algorithm is actually not rewarded when it brings out a lot of good answers. So these were weaknesses, and the author said, we can probably design a learning signal, meaning a loss function, that avoids the trivial solution, the possibility of cheating, and that uses the signal present in competing answers. How can we do that? We can build a system based on discriminative training. What do the authors mean by that term? They just came up for it, for their solution, so it's not a technical term to recognize or so. They call what their second solution discriminative training. What do they do here? We put in the numbers. We have our heuristic segmentation. So we have the graph with all the different segmentation ways. We have our instances of neural networks that try to recognize what is on each image. We have the graph, the same we see here, with all the possible interpretations and segmentations in one thing. And now comes discriminative training. What do we do here? One path here is quite similar to this one. We kick out all the paths that don't have the correct result. So we throw away all interpretations that our algorithm so far produces that are wrong. We just let those through that are correct. So this is again a constrained interpretation graph here. We use the Viterbi transformer just as here. We come to the same result. We sum up all the penalties. This is the first part of the loss function. But we have a second part here. And there will be a discriminative training between those two. What is the second part here? So this side is exactly like that side. That's the Viterbi training. What do we have here? We don't have the path selector. So on this side of training, we are just looking via the Viterbi algorithm for the path with the lowest overall penalty, regardless of if it is correct or not. Okay? Here, we are looking for the path with the lowest overall penalty that is correct, has the correct end result, the correct number. Here, we are just looking for the path with the lowest penalty. Our loss function then is the penalty from this side minus the penalty from this side. If the best correct path is also the best overall path, then this thing will be 0. And only then this thing will be 0. If there is another path that is not correct but has a lower penalty, we will have a positive loss value here. And this loss design forces the system to actually push all the solutions that are correct, to produce more solutions that are correct. Why? It uses more signal from what you actually, more signal to learn from. It uses all the solutions in the learning graph. It probably, to understand that completely fully, it needs to read that section of the paper, which is roughly five pages. But it's not too much about the system here, the specific system. What I want to show you is designing what I think in the first lecture we called it experience, or in the second lecture, what the experience for your learning algorithm is, what actually it has to learn from. That means how you calculate the loss plays a vital role in the design of the whole system. Here, between these two versions, is not too much difference in terms of architecture of the system. The neural network design is completely the same. Here it's not even printed. The whole approach, if you would describe it in an abstract, would be exactly the same. But the thing is, this system was used to automatically transcribe 50% of the US checks in the banking system. And this system would have been usable for nothing. And the difference is designing the learning experience. So if we talk about system development, there are, besides the nitty-gritty details you read about in the exercise before, that are also important, there are certain steps where it's really important to think about. And this is how you design what your algorithm should actually learn. Is it possible for the algorithm to cheat? Here it is, here it's not. Does it learn from everything it can learn from, or does it just ignore some things? Because usually you cannot afford that the algorithm does not learn from something that it could learn from. So there are several things we can learn from this check reading application. More boxes here. Okay. One thing is that this discriminative training has brought some success in that specific application. The other thing is that the end-to-end training brought a lot of success. If we go back here, that this whole pipeline of things, segmentation, recognition, assembly, is trained with a single loss function on top, and then everything is done by gradient descent, made the whole thing a lot easier for the system to learn, because humans didn't need to design that interface. We can learn from how the loss is designed, we can learn from how this pipeline is assembled end to end. I want to go to some conclusions I can draw from that. I told you the paper is from 1998. I read it about 2013, 2014, around that time. And I was completely amazed and fascinated by that paper. Because first, it explains CNNs, which lots of other papers tried for me, and only this one succeeded. And it showed a great big picture of how to design a system of an application where I thought that would not have been possible 20 years before. So I liked it a lot. At the same time, we were working on two machine learning systems that should accomplish, let's say, similar tasks. Also document recognition. One was to transcribe documents of written music into music XML. And another one was to disassemble a newspaper page into the constituent articles. And my idea back then was, let's take the learnings from that paper and build end-to-end systems. For example, a system where we don't need the intermediate ground truth of the crop marks, where we can just end-to-end learn from input, a page, output, all the articles. I mean, we saw in the last system, right? We don't have to have ground truth for the segmentation. We can learn that end-to-end. That was the idea here. Here also, my idea was how we could go from symbols on an image directly to a music representation for computer, maybe to MIDI or something like that. And we discussed that in depth in the research team. And luckily, my researchers convinced me that we should not try that. That we should, in that case, not do it fully end-to-end in, let's say, a naive way. We didn't try it in the end, but I guess it wouldn't have worked. Why? Because, and this is also an important part in system development, because there is an easier way to do it. Yes, it would be nice if we wouldn't need crop marks for all the articles and do it with heuristic over-segmentation and like in the system we did it before. But actually, we had some crop marks, not too many, but for 500 pages or so. And we could build, and I think it's the first reference here, we could actually use these 500 crop marks, build a fully convolutional neural network architecture, and arrive at a system that worked really well. And by this, we could use all the ground truth, all the learning signal we had. If we would have ignored this ground truth, this learning signal, I doubt that it would have worked better. So, and it was quite similar here. In the end, it worked really well. We have a nice publication on it, and research is still ongoing. Currently, just the follow-up project started, and we're really excited about that. And I doubt that we would have succeeded if we would have followed the naive idea of, oh, let's just re-implement the whole pipeline end-to-end without intermediate steps and everything, just going from symbols to basically XML source code. What do I want to tell you with this? I think one of the blog posts you read in the earlier exercise says, don't get fancy. And in the previous thing, I told you about the benefits of end-to-end learning, but I also told you don't ignore learning signal that you have. Use every bit of information you can get. If you can do something easy in machine learning, don't try to solve it complicated. If you have data for something, ground truth for something, use it, don't do it unsupervised if you have the supervised data. You can still use unsupervised for those problems where you don't have data or not enough data. End-to-end learning is a good idea, but if you have any prior information that might help your system to make it easier, build it into your system, build it into the architecture, it will pay off. This stuff is complicated enough with lots of challenges that might break the performance of the system, that you cannot afford willfully ignoring input that might be helpful. You can still get more fancy as soon as it works, but first make it work. In summary, usually our machine learning systems are pipelines of different steps. You can develop them alone, you can develop them in a team, you can develop them with distributed teams, doesn't matter. You have seen some tools here, most of them were just applying your common sense of how you can decide what makes sense to focus on. Look into your errors, look into how your different pipeline components contribute to the error, focus on that. Looking into the errors really means looking into the data. Don't forget that. Read the misclassified texts, look at the misclassified images, listen to the misclassified audio snippets. Like, look into the data. End-to-end learning is a very interesting thing. I think it became much more normal with neural networks, but the word of caution is don't get too fancy. Now, we will probably make a break. And then I will let you discuss the following exercise. And I will explain it briefly before we go to the break, because then we have all the talking. I will again let you read something quickly, not completely thoroughly and full in detail. And then I want you to discuss. What is it about? It's more about the big picture. There was a very fascinating article I read a couple of weeks ago. Co-author is the CEO of Google DeepMind, who at all occasions publicly announces that he likes to bring artificial intelligence more towards general questions. This is his. I'm not sure how far he can succeed there, but the research is very interesting. What does he propose? He writes an article for neuroscientists and cognitive scientists and psychologists, where he explains current breakthroughs in reinforcement learning, so one part of machine learning, and explains how this could help to better explain how biological learning works. And then he does the other way around and connects these findings in machine learning with what we know from psychology and from cognitive science works in biology. And I want you to do two things. I want to read you this article first, because next week, no, in 2 weeks, we will talk about reinforcement learning. And we will just have 1 week for it, so I want to give you the opportunity to read a little bit more about it. This article is geared not towards machine learners, but towards neuroscientists. So it is a very gentle introduction also to reinforcement learning. So it's a good overview, good start. That's the first reason. The second reason is it gives you a bigger picture. How learning in biology and learning in machines is connected. And I want to give you that aha erlebnis. What is that? Aha moment. This welcome moment. So don't spend too much time with it. Briefly skim it, take 20 minutes, 25 minutes, read it, and then start discussing with who's sitting at your table. What reinforcement actually is. Why is it something different? What distinguishes it from the rest? What does Hasabi and his colleagues actually mean by slow learning, fast learning? Why is it a problem? Why is it a problem in machine learning? Where have you experienced it? Look into these questions, start discussing it. It's an open-ended thing, and you don't need to stay for hours, but use this as an opportunity to widen your field of view. I thank you for today, and wish you a good break.